Welcome back. Today, we're diving into the final showdown in our database masterclass. We're pitting two absolute giants against each other, the write-heavy hero, the LSM tree, and the read-optimized veteran, the B tree. Let's get right into it. All right, team, day 25, let's dive in. Yesterday we built a monster, a write-optimized beast to be exact. We took on the challenge of high-speed writes, and we won, creating what's called a log-structured merge tree. Our write-heavy hero, yeah, remember this? Our LSM tree is blazingly fast for writes because it never modifies old data, it just appends new sorted files, our SSTables, sequentially. It's simple, and man is it fast. But that incredible speed, it comes with the hidden cost, a pretty messy secret our database has been keeping. See, because LSM trees are append-only, every single update creates a totally new record. So think about it. If a user updates their profile, say 10 times, we're not just editing one file. Oh no, we are hoarding 10 separate copies across 10 different bricks. Okay, reality check. What happens when you actually want to read that user's profile? Well, the database has to dig through that entire messy pile, from the newest brick all the way to the oldest, just to find the latest version. Reads get painfully slow. So how do we fix this mess without killing our amazing write speed? Well, we bring in the janitors. We initiate the great compaction. This is compaction. You can think of it as a background garbage collection process that just cleans up the mess we've made. And this right here illustrates the power move perfectly. The database takes that whole stack of old messy bricks, crushes them all together, and spits out one ultra-dense, perfectly organized super brick. All the junk is gone. And during this merge, the process is absolutely ruthless. It throws away all the outdated versions, any duplicate data, and special deletion records we call tombstones, which basically just mark a key for removal. So compaction is a really great solution, but let's be real. It's a solution to a self-inflicted problem. What if we just never made a mess in the first place? Well, let's meet the rival, the B tree. Yeah, the B tree, the neat freak of databases. This is the storage engine behind pretty much every traditional SQL database you can think of, like Postgres, and it is the total philosophical opposite of our LSM tree. So instead of piling up bricks on the floor, the B tree is like this pristine, neon-lit filing cabinet. The entire database is organized into these small 4-kilobyte folders called pages. Now, what's really fascinating here is the core difference. A B tree doesn't append. It performs what's called an in-place update. A robotic arm locates the exact 4KB page with the data, opens it up, erases the old value, and writes a new one right over it. Then it puts that updated page exactly back where it found it. No mess. So there you have it. We now have two completely different ways of handling data. One is a speed demon for writing, the other is a meticulous librarian for reading. This is the ultimate trade-off. And this leads us to the final showdown. And here is the kicker. This is the one rule you absolutely need to remember. Look at this! LSM Trees group writes into these sequential chunks, making them incredibly fast, perfect for write-heavy apps like Cassandra. B trees, they have to do a bit more work to write, but, and this is key, since every piece of data has exactly one location, reads are consistently lightning fast. And that right there, that is the ultimate rule of thumb straight from the source material. And why does this matter? Oh, it's simple. Choosing the wrong engine for your workload can be an absolute performance disaster. So now you know exactly which database engine to choose. Awesome. But what happens if half your servers suddenly lose their internet access? Do you shut the app down? Or do you serve old, stale data? This is honestly one of the hardest questions in all of distributed systems. And tomorrow, we're going to answer it by diving into the CAP theorem. It is an absolute cornerstone of system design, and you do not want to miss it. Make sure you hit subscribe. I'll see you then.